I've started the recording, Maharshi. So
Okay,
when you're
great.
ready, you can start.
Okay, no worries. 2 minutes are there. And if you could just show your video when we start, Rita, I would like to recognize your contribution. Um, so 2 more minutes, we'll start. Once again, please leave your name and association name and the country name. This webinar is offered to IOHA members for free. If you are not IOHA member, and if you have not paid the minimum fee which is required, in that case, please log off. Okay. We have 48 participants as of now. Rita, chat, I'm sure the chat is available, so we'll be able to make out how many countries participated. But later, if you can just send me some information while recognizing Bob Johnson, we'll mention how many countries and participants attended the webinar. All right, good morning, everyone. My name is Maharshi Mehta. I am immediate past president of IOHA. As of 22nd of October, we had an AGM and the board meeting where Samantha Cornell has become president. IOHA is associations of associations, as you may be knowing. We have 42 associations now, about 20,000 plus members of each associations. As a part of actually our service to IOHA members, we have started offering this webinar since last year and a half. About 18 webinars are offered. This is 19th webinar. And these webinars are taught by top-notch faculties. And topics are also very much relevant. We had lots of enthusiasm from members around the world. I would like to recognize Rita, who is, she calls secretary, but we think that she is an administrator who is supporting all of us to do what we do. I would like to make a pitch about what's happening with IOHA. We have a conference in Nigeria coming up. So if you are around Nigeria, please go ahead and talk to Matthew, who is here. Also, 2024 IOHA conference is going to be in Dublin, and Rita will insert a link here. I would encourage you to register for the conference. There will be several PDCs, and all that information will be coming out. If you have any question about this webinar, please leave it in the chat section. And later, after about an hour and a half, so about 1 hour of the presentation will be there and 15 minutes of the discussion and question answer. So leave your questions in the question answer session as Robert Johnson is speaking. Bob Johnson has been outstanding speaker. He has more than 20 years of experience in non-ionization radiation related subject. He has been member of IOHA and number of other society uh, for non-ionizing radiation. He already offered this webinar one time before, and response was outstanding and overwhelming. That webinar we offered during the evening hours so that people from Australia and other countries can participate. This time we are offering during the morning hours so people from Europe and Mexico and hopefully California and other countries can participate. With that introduction, Rita, is there anything else we need to communicate before we have Robert Johnson start the webinar?
Oh, we can start.
Okay, wonderful. Once again, we would like to recognize Robert for your service to the association. Okay, with that, I will let you start the webinar, Robert.
Okay, well, good morning, good afternoon, good evening, good day, whatever. We're depending on where you are. So thank you for attending. As Maharshi said, I've been involved in doing presentations and the education side for quite a few years. Work on the AIHA's NIR committee, the Non-Ionizing Radiation Committee, and also a member of IEEE for years, working on the C95 group of standards and guides. As I always say, we're ISIS, but we're the good ISIS. We're the International Committee for Electromagnetic Safety, so ICES. And we come out with various, not just limits, but we come out with safety program standards and some other guides about how to do measurements and other particular things. So we work closely with ICNR, and we have some members that are on both committees. And so that's what we spend our time doing. So anyway, some of the presentation here, see how this works for you. So just some of the subjects, hopefully everyone can see it. You know, not all sources require surveys. If you look behind me, you'll see a little Wi-Fi router, as we would call it, an access point. And this is very low power. Yes, it generates non-ionizing radiation, but we don't waste time for it because it is what we call like type approved by our government. And so we don't waste a whole lot of times measuring those things. But anyway, we'll go through that. And some of the standards and guidances, some of the documents that are out there are very good. Most, if not all, are available for free. And there's a lot of good things out there. So I know, some of the people from Canada and Industry Canada, I forget what they're called these days, but they've come out with some documents to support Safety Code 6. Like I said, in the IEEE and the FCC, there's various documents for people from the US side. And some of the ITU documents, I think, are very good. And I reference those as well, I think, in this presentation. So we'll see how to do it. So when to measure, and of course, safety programs, like I said, a lot of times ICNR will put out limits, and then you need to look more at the IEC or the ITU for help in developing a standard procedure, a policy to follow. Within the IEEE this last year, we took what was a recommended practice and made it a standard for safety programs. And those are available for free to download as well if you want to start or adapt your thing, program, as it were. And then some of the controls that we use, like any hazard, we can't always eliminate and substitute, but we talk mostly about engineering controls and warning systems and administrative controls that are kind of typically used in this part of the spectrum, let's say. And I just had one of the presentations I did, and someone asked, well, what about getting a consultant? And of course, we all do that quite a bit. And so I just kind of put out some hints and tips for consultants if you're going to go that way. So the spectrum, right? So when we look at the spectrum, we start out in electromagnetic fields. A field, non-ionizing radiation, something is radiation if it has an amplitude and as well as a direction. So something is radiating, electromagnetic radiation. So everyone knows kind of MRIs or high energy research, where we're using very strong magnets in those areas. So we've got static fields, and then we start alternating, much like 50, 60 hertz for power. And then we get up into the typical radio frequency and microwave region. Um, technically, microwaves are anything that have a wavelength of less than a meter. Uh, Although, the public, because a lot of the public sees the heating done by a microwave oven, one of the most common sources, they think that is something different than radio frequency, and it really isn't. It's just that it is at somewhat of a shorter wavelength. So nothing else special about being microwave. Um, but television and radio and all the things that we kind of like. And then, of course, we get into the cell phones. Today's technology, the new 5G, has presented some interest safety wise. The fifth generation of cell phones are really not that much different than the fourth generation of cell phones or the third. Um, the 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 smart thing about this, and we'll talk a little bit about it, is that the phones are able to take bits and pieces of various frequency bands and put them together to give you bandwidth. Bandwidth determines the overall speed. So if you have a larger pipe, if you will, you have more water flow through that, and it's the same idea for cell phones. So cell phones and the technology really haven't changed that much in this new 5G world. But there's anything new is somewhat troubling sometimes for people, and so we get more interest in 5G, of course. Um, Satellite, of course, we're all used to satellite systems, whether it's satellite TV, satellite internet, uh, Elon Musk and Starlink and things like that, which works well for a lot of people. And if you're in a very remote area and you can't get internet any other way, it's a pretty good solution. I have to say I am a customer. So not here, but we have a place in rural New York, and it helps quite a bit, I guess I'll say. Anyway, so then we get above the microwave region, we get into what we call the optical region. So even the ACGIH standards, uh, uh, will reference, because we get agreement between ICNIRP and ACGIH, this harmonization of recommended limits. And so when we get into the optical, people know it as infrared bulbs, infrared heating lamps, of course, daylight that we see, and into the ultraviolet region. We start getting a different effect, and then of course up into the ionizing region. So, and in the world of ionizing radiation, and I know we've got some people here that know a lot more than me in that region, but the dose as well as the dose rate is important. And in the non-ionizing world, we don't worry so much about that. We worry about essentially short-term heating. So the difference for us is that once we get an exposure to non-ionizing radiation, as long as it's below the limits, it can be continuous, but if it goes above the limits, we keep it to a shorter period of time so that we give the body some time to cool off. More about that as we get into it. But non-ionizing has a much different effect than ionizing does. And so at any rate, I give in this chart, you'll see the idea of induced currents or heating, the effect of it, or surface heating. And then the frequencies and wavelengths that you're exposed to in these different regions. And the only interesting part I think to note about this is that years ago when we set up standards for RF and microwave type radiation versus optical, is we could only count frequency up to about 300 gigahertz. And so that's why typically we don't discuss like a laser pointer in terms of its frequency. We part of the classification is like what the wavelength is. So wavelength is important, but frequency, and like I said, we just changed the description of that once we get into the optical region. We go more with wavelength than we do frequency. But at any rate, that's kind of the spectrum as we hop across it. And some of the effects, this is a generalization, but hopefully it lets you understand a little bit more of what the exposure effects are. And when you start down at DC to maybe 3 kilohertz, in that region, the body is the permeability, if you will, that would be the term, of the tissue is equal to that of air. So there's no absorption because the body is invisible to the magnetic field. And so the magnetic field doesn't perturb us as humans by ourselves. Where the issue becomes for a lot of us in safety is if a person has an implanted medical device. Implanted medical devices can be affected. And so since the body provides no shielding at all, that could cause an issue with those kind of devices. But, when you and I go to the airport and we walk through the whole body scanner, maybe the magnetic field, it's really what we would call a magnetometer. And when you walk through that device, you should not perturb the field at all. And so the security people are looking up at a bar graph as you walk through, and they are noting how much you perturb the magnetic field. And of course, they set alarms based on that. That's one method of security detection, using the electromagnetic field for that. And some of the others are actually microwave radar. Some of the active systems where you stand with your hands up and empty your pockets, and they utilize a very high frequency, up around 38 gigahertz. And there's 10 little transceivers on the bar as the bar swings across your body. And that obviously bounces fields off the body, and it can detect if there's hidden plastic material, or of course metals or something like that. So that's using non-ionizing radiation and examples for safety, and we do a lot of that. So anyway, DC to 3 kilohertz. And the interesting part is the electric field is totally blocked by the body. We perturb the electric field. There's no absorption because of the permittivity of the tissue as opposed to the permeability. So below 3 kilohertz, the levels and limits are relatively high, very high, as opposed to RF microwave because of this absorption effect or not absorption. Once we get above 3 kilohertz, up into the region of kind of 100 kilohertz and maybe a little bit more, there is some absorption that starts. The electric more than the magnetic. The levels and limits, again, are very high. I know, like, again, an example would be safety code 6 for the Canadian people here. The standard basically says, hey, the magnetic fields we allow are so high, and you can just determine compliance by just doing the electric field, because it's almost hard to measure such a high magnetic field in that area. But in this area, like we said, induced currents, and part of these are things called like eddy currents and heating metals. So I know it's probably not a good picture, but if you look at these loops, you have these coils around a metal bolt and nut, and you're heating that up very red. And in fact, there are new, if you're into tools and working on vehicles, there are new induction heating, it's called, tools, battery operated, that you could work and put on a rusty bolt under a car if you have the room, and that would be safer in most cases than trying to do it with a torch, igniting some fuel, whatever, leftover oil or gas in a vehicle. So you can actually heat up things with induction. And the same scenario technology is for what's called induction stoves. So I don't know if it's a thing where you are, but certainly it is in the United States, where we're using this induction principle to heat the metal, and then whatever's inside the metal pot or pan gets heated because the metal warms up. So we're not heating what's in there directly, we're heating the metal itself, and that in turn heats the contents. So induction stoves, you could put your hand on an induction and you wouldn't feel anything. There wouldn't be any heat because of the frequency that's used. So it's a technology, So I see one of the questions here, what should one do if observed microwave emitting energy waves through leaking? Well, microwaves are typically type accepted, and a microwave oven, if it's going to leak the energy, number one, you would feel it because it's a much higher frequency. And number two, it's usually because of the price of the device. These days, it's usually just a case where you replace it because it's too inexpensive to repair, whatever. Arc furnaces, they usually don't emit ultraviolet to my knowledge, but they do emit, of course, induction kind of frequencies. And an arc, like arc welding, if you will, that puts a kind of a group of emissions across the lower frequency region. So that may be something that goes from close to DC up to hundreds of kilohertz, typically, arc induction, like in steel, remelting of steel, and things like that. Some of the factories that I've been to, it's been kind of a very strong electromagnetic field exposure, not just from the induction heating itself, the furnace, but from the lines that supply the current to the arcing device. So a lot of strong fields around those devices. So, at any rate, and once we get above 100 kilohertz or so, if you look on the slide, we talk about the range of SAR. And so SAR is what we call specific absorption rate. So there's a range of frequencies where the body does absorb the energy. And that amount of energy creates heating in the tissues. And so standards, whether they're safety code 6 or whether they're ICNIRP or whether they're IEEE or FCC, they are based on the overall heating effect. Now, it can be heating over a small part of tissue, and we have partial body limits for that, and then we have whole body limits for the body as a whole. And so at some point, as you might expect, at some point there's absorption, there's enough absorption of the field to heat the tissues to where you could possibly overload, if you will, the thermoregulatory system and its ability to cool the body and to thermoregulate tissue temperature. And so that's what standards are kind of based on. They're based on other effects, but a main part of exposure limits are based on the heating effect. And so what we call SAR, so from 100 kilohertz up to about 6 gigahertz is where any devices, that generate these fields, they can create heating. And all of us, you'll be happy to learn, I know, all of us are antennas. And so all of us have what we call a resonant frequency. Based on our height, there's a frequency that we absorb energy at better than any others. A standard, typical 1.75, whatever, meter tall adult, it's something around 80 or so megahertz ungrounded. And when you stand on ground, the closer you get to actual ground, then what happens is you turn from a monopole to what we call a dipole. There's an invisible U beneath the ground, and now you've doubled your electrical length, and then your resonance shifts down in half. And so when you look at ICNIRP or ACGIH or IEEE Safety Code 6, when you look at any standard, what you'll find is that in the area of about 10 to 400 megahertz is the most restricted in terms of levels of fields. So it's not the microwave frequencies, it's actually this radio frequency area and the VHF, you might call it. That's where the highest absorption takes place. And so in certain documented overexposure situations, because the depth of penetration can be quite deep and very little sits on your skin. And so there's many documented cases of people being overexposed to, let's say, a FM radio station around 100 megahertz, and they were there for too long and didn't feel it. Whereas at microwave, you would most likely feel it right away, very quickly, but with this depth of penetration. So that turns out to be one of the more critical parts of the spectrum, because not only is our absorption the highest, but our recognition of being heating is also not as good as it would be again at microwave. And we'll come back to that. But so SAR is a big point. Every one of your cell phones was tested. The type of cell phone was tested by the government, by the authorities, and approved before it's allowed to be sold in your market. So in America, it's the FCC. In Canada, I forget, but I think Industry Canada does that kind of testing. And so we all have a government that, again, watches over us and specifies levels, and then people have to determine compliance with that. So everything is tested for SAR. All the Bluetooth devices we wear, all of the phones, the tablets, the laptop computers, all of these things that, communicate at 2.45 gigahertz and 5.8 gigahertz and other bands. They're all in this range of SAR. And so that's kind of what's going on in that area. Once you get above 6 gigahertz, then there's not much in the way of absorption. Now we're just talking about surface heating. And so again, surface heating is can be annoying to, bad, and of course produce burns. And so that happens in the higher frequency. So the higher the frequency goes, the less of the depth of penetration. And again, if you think of like infrared bulbs, if you stick your hand under an infrared bulb, you instantly know the direction that the heat is coming from, and you usually detect it immediately. If the bulb were strong enough, it would hurt or it would burn, and of course we don't like that. So that's where you get into that region. And then again, up into the ultraviolet area, you've got your tanning and your burning rays, and then of course the dangerous UVC. Now UVC, for some of the people that might be semiconductor, it's one of the easiest to shield, actually. Like a Pyrex glass is a very good shield for UVC. But as an example would be, as our semiconductors work to become smaller and smaller and operate faster and faster at higher speeds, the semiconductor industry is getting very close to, they're in the UVC region, but some of that is getting very close actually to ionizing radiation. So the semiconductor, at some point, those again, the wavelengths are going to get smaller and smaller in order to make, if you will, a transistor smaller and smaller. That's when they'll probably bridge and then be worried about ionizing radiation rather than non-ionizing. exposure to furnace, what should be the recommended distance? I'm just reading a commercial in the chat, so the furnace be one recommended. Really depends, right? So I'm not sure, and that depends on the fields, right? So it depends on the design of the furnace. There's no real set limit to my mind as to how far someone should be kept away. I mean, we have a slide coming up and we talk about time, distance, and shielding, the basics of radiation exposure control, ionizing or non-ionizing. And so what I don't know from the furnace questions, I don't know the distance that should be. Like I said, when I was at one steel mill, where they were remelting steel, and you know, basically recycling it. The current feeding those electrodes was so strong that a medical device person, I would think, would have to be kept many meters away, maybe like 20 or 30 meters possibly. So, you know, in certain situations, you'd have to keep people that far away. Now, regular human limits, I don't want to call them, but the standard limits would be something where you could keep people 5 meters away, 3 meters away would be kind of the distance. So it depends on the amount of current that the induction furnace is consuming, what it operates at, as to what kind of fields that are going to be generated, and then what the distances should be. So anyway, so this is just so you get an idea of the exposure effect versus frequencies. And one of the things, again, I may or may not have said, but like microwaves, when you know, like a 6 gigahertz satellite communication, if it's strong enough and you put your hand there, you will immediately feel the field. And so the body, because a majority of the energy is deposited close to the skin, you feel that energy. And it's much like sunlight, right? I mean, we get light, and if a flashlight is strong enough, we can hold it against our skin and feel the heating. And that's non-ionizing radiation. It's not that different from the frequencies that we don't see. So it's one of whether or not you get that notification from the body. And so again, to my mind, microwave overexposures are probably more uncommon because people would feel it and they would react. Animals thermoregulate for the most part. So that's one of the things one should think about. But anyway, so again, significant sources. One of the things that I propose to you is based on SAR, specific absorption rate limits. If you take a normal 70 kilogram body and you take 5 watts and divide into it, the numbers, the result of the math is that you will still be under what I call the untrained worker or general public limit. So generally at what I call lower frequencies, less than 6 gigahertz, is it might be a good number to use something like 5 watts in your safety program, right? So whether you have a safety program or you're looking at improving it, you don't want to measure every source of non-ionizing radiation, like try to show it here, like my Wi-Fi. I don't worry about it. It's 100 milliwatts. It's not even a watt of energy. And so it's very low powered comparatively to what a human can absorb and what could affect. So I typically recommend to most of my clients that you set a level of about 5 watts up to 6 gigahertz, and then maybe above 6 gigahertz, use 1 watt. And so in engineering, and I'm an engineer, I'm not an industrial hygienist by training. And, you know, we use in engineering, we use a lot of things called signal generators, spectrum analyzers, vector analyzers, and we use a lot of what I call low power test equipment. And I don't want to go into a company and you know, a larger company may have hundreds of these devices, and you don't want to waste your time making a program for them because it will just eat up all your time. And quite honestly, it's just not a source that can affect people, no matter how it's used or misused, because the power level is not high enough. So I think in terms of frequency and wavelength and power, that you should have some cutoff to your program of things that you're not going to worry about. And a lot of the things like radios, handheld two-way radios, are what we call type accepted by the government. And so they've already been accepted for sale and use by the general public. And so I would, like I said, I would not put a program around those things. It's not perhaps the best use of your time. And then frequency and wavelength, we talk about energy. So from a point of photon energy, as the energy increases, as the frequency increases and the wavelength decreases, the energy increases. So once we get around in the upper ultraviolet region of the spectrum, in the US, we use around 12.4 electron volts. The UK may use something, I think, around 10. Some people may use 15. It depends a lot on temperature and some other factors. But that's where you can start. You have enough energy to ionize material. So you could create free radicals. You could separate maybe hydrogen from oxygen. And so that is where you go from non-ionizing to ionizing radiation. And so that, you know, increases. And of course, ionizing radiation. Now we've got the wavelength and the photon energy to have a different health effect than we do in non-ionizing energy. So if it's a million watts, a megawatt of energy in non-ionizing, the effect that it can create will be, the speed will increase on that, but we still can't have the same health effect as ionizing radiation. So we're quite a bit different from that. So that's why our standards are more based on a short-term heating effect per se. We talk about names and labels and that identifying significant sources. So you may have things like an amplifier, you know, or an antenna or a transmitter. There's various names like that are recognized, and you may recognize and say, oh, okay, well, what power level is that amplifier? And I want to know this. So there's some hints out there about the name of certain devices. And like I said, it's interesting that the induction stoves, when you think of an induction stove, I think most of the general public, if not all of them, don't really know what induction means. But I think if you called it a radiation stove, it would be much harder to sell it, right? So you don't use the R word. You use, you know, radiation, you know, even the name of my company, you know, EME safety, electromagnetic energy. So it's kind of what it stands for. But I don't use radiation because when you use the R word, people tend to think, and rightly so maybe, that, you know, that you're all talking about ionizing radiation. And so that's something that the press and the news media and everybody get wrong. And, you know, that's just what they do, right? So at any rate, so names and labels may help you in identifying sources. And then the condition of equipment, as I call it, like when you take things apart, if you take things apart to service them or to repair them, then a lot of times the pieces all need to put back together before you turn them back on. And so I work with certain industries, and humans are forgetful. That's just the nature of our being. And sometimes the shields are not put back correctly, or may perhaps missing. And so the condition of equipment can of course have a large effect on your program and the fields and the things that you measure. So I throw that out there also. So these are kind of ways to identify significant sources. Certainly power level is important, frequency is important, what does it operate at, and of course names and condition and things like that all affect what we're doing. For most of us here, we're going to follow the, if you will, the recommendations of ICNIRP, right? So ICNIRP is the International Commission for Non-Ionizing Radiation Protection. You know, they've been around for decades as a group, and their latest RF and microwave limits were released in 2020, and they agree greatly with the IEEE. We are, in the world of non-ionizing radiation, we are very close to harmonization, if you will, an agreement across the entire frequency range between the groups. Now, to the two major, I think the two major groups are ICNIRP and IEEE, in that we do an exhaustive literature review of every paper. We identify the author, we identify the results of the program, we look at how was it paid for and by who, you know, were the right results, you know, derived from the study. There is good science and there's bad science, as you might expect in any industry, and we get the same of it in the non-ionizing radiation world. But certainly IEEE and ICNIRP have a whole group doing this now. ICNIRP is a relatively small group who are not involved. They typically are all, if you will, academia. They are not involved in the industry. In IEEE, we're more a larger group, and we are part of industry, if you will. Excuse me, my phone goes off here. Apologize. Come on. There we go. So, at any rate, that's the difference. Now, Industry Canada, Health Canada, Health Canada does the same thing. They look at, I know they look at what papers I think are identified between IEEE and ICNIRP, and the results, and review it, and do the same thing, and typically do it, you know, for Canada. I think, and my little commercial is, I think that once there is harmonization between IEEE and ICNIRP, that Canada will follow. They will join the rest of us, and we will have what I consider at that point, we'll have worldwide harmonization, really one set of limits. We're all one group of people, and we're very close to that level. So at any rate, ICNIRP is very similar to, again, IEEE, FCC, and Canada Safety Code 6. They use the terms occupational and general public, but if you review some of the ITU or IEC documents, they talk about really trained workers versus untrained workers. And so in Canada, in the States, and really in the rest of the world, we look at the differentiator being the trained employee, and then the untrained employee is the same as the general public. And that's the way the limits are going. We have two different limits. My own feeling is that the trained employee limit is based on science, and the untrained general public limits are more based on politics, quite honestly. There's not something that says, you know, that if you're the public and you're there for 24/7, that you should have a lower exposure limit, but that's what we've done. And you know, again, sometimes it pays to be politically correct versus technical, but the definitions really get into it. So it becomes a legal issue in Canada, certainly, as well as the United States. I don't know about your country, where you're coming from or attending, but we, like I said, we have this trained employee what we call a controlled environment in Canada. We call it a restricted environment or an unrestricted environment. In a restricted environment, we expect people to be trained, and we expect them to be able to make an educated decision about what they're doing and to be educated. And so we don't use this occupational and general public. And again, even I think ICNIRP is getting away from that. So again, best practice for you in your country would be to look at and say, okay, well, we've got this area for, where we're doing RF work, and we have our engineers and our technicians, and we train them on RF radiation safety. But we have this other part of our company where we have, if you will, clerical people and non-technical people, and we don't train them. So we keep them out of this area. So we have a restricted area and unrestricted access the rest of the company. So that's kind of how we do limits and levels. The workers directive, again, which ends up being a directive, ends up being law. In America, we use different English per se. We have standards, and then we have regulations. So the regulations end up being law for us. Contact and induced currents, in some cases, in some frequencies below resonance, so below 100 megahertz or something like that, you could induce current into the body, or you could touch some metal and you could contact where radio frequency current would go through you. And we limit that amount of current. So not just the field exposure, but the resultant currents of our exposure. And again, basic restrictions in terms of SAR. So all of the standards, and again, Safety Code 6, ICNIRP, IEEE, what we say, well, the basic restriction, the basic limit, what we're really talking about here is SAR in this certain frequency range. You can exceed the field limits if you can demonstrate that the SAR has not been exceeded. Now, that's what we would call in American slang a catch-22. It's hard to expose an employee above a certain level and then prove that you didn't exceed their SAR. Really almost impossible. So these field levels become kind of a limit that we deal with, because this is, like all the commercials, or the questions here in the chat area is, what level and what we can be measured, what can we measure out in the field. So a laboratory is one thing, but you and I and everybody involved in this kind of safety, most all of us are only going to be able to measure the fields with the proper equipment. And so fields are what we do. And so just so you know, when you look at the standards, we say, well, that doesn't necessarily mean you were overexposed. But I think what you'd find in most cases is the field limits are the limits that you and I deal with. So, at any rate, so outside what I call North America, right? So, yes, in the United States we have the IEEE, or we have FCC. In Canada they have Safety Code 6, but really the rest of the world, I'm aware of no other country that follows IEEE, FCC, or Safety Code 6 limits. I could be wrong, but pretty much for the most of the rest of the world, ICNIRP is the recommended, the guidance that everyone follows. And so you can go to icnirp.org and you're free to download recommendations. And like I said, my only concern about ICNIRP is we don't really have like, okay, well, how do I comply? We don't have that safety program standard or the safety program recommendations. Yes, we have documents from the ITU and the IEC. And for most of you, that might be normal. For us in the IEEE, we like to have the limits as well as the standards on how you comply with the limit. And so that's the whole group of C95 limits. And so you might find, for some of you, I know I have a slide on it, but for some of you might find it very educational, I guess. And again, for what limits applied, again, an RF worker or an RF informed worker. You know, this is kind of what you would look at. You know, you're performing some risk and exposure. You're training the workers, providing information on them, what we do. Hey, I put signs up and here's what it means, or I put a barrier up and here's what it means and who can go in there. And again, providing workers with the right tools in terms of perhaps equipment or perhaps education as part of the right tools in applying preventive measurements. Now, you know, it may not include pregnant women. This is from the ITU document. This is, you know, if people are with child, it may be that an exposure to the occupational levels, maybe it would be prudent to limit them to the untrained worker or the general public levels. So that's for you to decide. But, you know, implanted medical devices are some of the same things. So it could be an insulin pump or pacemaker, or, you know, it could be, there's various things. If you look in American TV, there's various medical devices that are now implanted on or in a body for maybe automatic drug delivery or some other medical situation warrants that. Those things can be affected by strong radio frequency fields. And so you might, in our country, we cannot ask somebody if they are with child, if they are pregnant. It's up to them to self-identify, I guess we would call it. Yeah, prosthetics, not so much the prosthetics. So, you know, I think of mostly the issue here is one of an active implanted medical device. So something with electronics, something that is operating. So it's active as opposed to an inactive. Now, for some of the people that were questioning the induction furnaces. So if you have an induction furnace, it is potentially possible that there can be strong enough magnetic fields outside that if you have implanted metal, costume jewelry or something like that, that it could be affected, and you could put enough current through the costume jewelry to heat the tissue around that item, if you will. So that's where it could have an issue. So you may want to see, and again, like most of it, at least for us in the States here, and I think Canada, we say, well, what's the advice of your doctor? So we look for the doctor and kind of put it on the medical industry and say, hey, is this something we need to do? So at any rate, I show you limits and levels, and I know this doesn't mean a whole lot, but in terms of limits, here I've plotted it in terms of what we call watts per meter squared, equivalent power density. I think if you look at the dark blue line, if you can see that, in the area, in this case, of like 20, 30 megahertz, so 30 up to 400 megahertz, is the most restrictive. And remember, that's that whole body resonance region. So we have the highest absorption. We could be, a 2 whatever meter adult, a basketball player, somebody proficient at playing basketball, typically very tall person, or it could be very short. You could be a newborn child, and you could be a fraction of a meter in wavelength. And so in order to be protective of all humans, that's kind of that most restrictive region that you see here in the chart. So it's not microwave, it's not the higher frequencies. We can actually take more energy because we don't have this peak of absorption. We don't have what we call resonance. And then get down to the low frequencies, and there's very little absorption at all. So the levels that we can expose to can be really thousands of times higher. So each one of these major lines, is like a factor of 10. So in about it. So yes, we will respond. So hopefully about ready. No, anyway, go here. Yeah. So some of the significant sources, just wanted to give you an idea, dielectric heaters that operate in this, and they're used, many are 27 megahertz to heat vinyl. So if you think of common vinyl like a blood bag where you give blood, it's a heavier vinyl and it's actually sealed with 27 megahertz. So the vinyl responds very well to the current, the radio frequency current, and we call them like vinyl welders in a lot of cases. So these things are used in a lot of industries, medical device industries, and other industries to seal vinyl, heavy vinyl. Semiconductors, your loose tube may be sputtering or plasma etching, and they operate at about exactly half the frequency of a vinyl welder, a lot of it at 13.5 megahertz. Induction heatings, when you think induction heating, you think of metals. So when we're heating metals for whatever reason, we're typically using induction frequencies to do those. And of course, we're all used to broadcasting AM, FM, radio, cell phone, base stations. There's a lot of that in our world. Rooftops become, in the past, the rooftops have been a very, very busy site in North America, certainly, for wireless transmitter sites. 5G systems will move them closer to the street, which is a whole different discussion, but that'll be part of what you'll see coming in the future. And of course, radar, weather radar that we watch the news with, and radar on some vehicles, of course, nowadays have essentially radar systems, very low power, but radar, nonetheless, radar principle, that if you're going to walk around the vehicle. And I think, like even Teslas, of course, have some of the radar with it. And then some of the medical uses, we would call it diathermy. So diathermy was using some of these different frequencies to heat tissues, so to do deep heating of tissues. So in some cases, it was, trying to heat tissues, and we're actually even going away, or, now there's drugs that can be inserted into the body with metallic particles and go to, let's say, like a tumor, and then the tumor can be unequally heated versus other tissues because it has these metallic particles in it. And so even in some forms of research, cancer research, we use some of this energy. So energy, again, we all maybe think of communications, but energy is used for heating materials in more efficient ways across the spectrum. So it's something that we do and use quite a bit in industry, beyond what you may have thought. RF surveys, when we do RF surveys, just so you get an idea, there's this electromagnetic field, and in some cases at lower frequencies and longer wavelengths, we're going to measure both the electric and the magnetic field separately. In some cases, we're just going to measure normally one of the fields, which is usually turns out to be electric. So the one thing I would say down at the bottom is surveys of unbounded fields and propagating electromagnetic waves are not a pure science. So the errors can be quite large. So any survey that's done, you do it or somebody else does it, it should include an estimation of the measurement uncertainty. So I'm going to do surveys today. As a matter of fact, I'm going to go down to Tucson for a client, Tucson, Arizona, and I'm going to be measuring, and I include like a 3 dB error in my results. So whatever your results, whatever your limits are, I'm going to add like 3 dB to that to make sure that my results are conservative and work. So surveys are not without errors. So I throw that out there. And This slide, just, again, nobody measures power density, but we all measure electromagnetic fields. We typically measure the electric field or the magnetic field, and then we convert it to something that people like as a unit. And I just throw out some hints in there, and again, minimum measurement distances and what we measure in certain areas. And so just part of this, the slide. So that should be part of your consideration as it is, what am I measuring? Now, to get away from RF for a second, kind of step into the light region. So, and basically for most of us, when we're looking at ultraviolet measurements, is it a coherent source or not? So a coherent ultraviolet source is a laser. So that is a coherent source. And then you've got laser TLVs are separate than the non-coherent source. And so we look at this, and it's just kind of a flow chart on these and looking at ultraviolet exposure. So again, semiconductor and a lot of the curing systems are using ultraviolet energy. Some of the germicidal applications, when I was a young man, decades ago, it was very common in a barber shop that they would have actually an ultraviolet light, and the barber would put the combs or the brushes or whatever under that for germicidal applications. So, in between haircuts, they would do this, and that's all but disappeared now. But it's using ultraviolet for, again, controlling germicidals. So anyway, controlling germs. So anyway, you can look at this flow chart. It's pretty simple. This is kind of based on the ACGIH TLVs, and I think it's very common. And again, there's this harmonization between ACGIH and ICNIRP. And so I think we all agree this is kind of the flow chart for those kind of surveys. So again, lasers are a completely different subject, but this will help you if you've got some semiconductor production or whatnot. And again, what are we doing? We're doing either wavelength, irradiance, and energy density. So again, we typically classify even infrared lasers, visible lasers, we classify them by the wavelength that they operate as well as their power level. And so with lasers, it's quite easy to have a class 1, 2, 3, 4 device and to divide it into the various classes, and then the control measures that you should put into that. That becomes fairly simple. We tried to do the same thing in non-ionizing radiation and have a class 1, 2, 3, 4 emitter, right? And it doesn't quite work as well as it does in lasers. So you'll see some of this, and it's like I said, it's based and it comes out of laser in that. This is again, so the different UV bands. So the old days of the black light, right? So the black light used to be common again when I was growing up many years ago. You'd get a black light for your bedroom, you know what I mean? And the glowing posters or whatever. But black lights are still good for some inspection environments. So, and of course, tanning beds and again, one of those things that I don't think there's a whole lot of people that do it, certainly not in Arizona, but maybe in some of the other locales, there are still tanning salons, I guess. You want to make sure that they're putting out UVA. If they put out UVB, well, then you've got more the chance of the sunburn. So now we have to worry about burning of the skin because of the higher frequency energy level. And then, of course, UVC becomes kind of dangerous. There you're talking about potentially cancer. And, of course, the lithography. So some of in the semiconductor world, the lithography is using the higher frequencies And again, like I said, is they're getting very close to ionizing radiation. Once you get above the UVC, you're now generating soft X-rays. And so as the frequency goes up and the wavelength goes down again, we get above this 100 nanometer, less than 100 nanometer wavelength. That's where we're going to bridge into the ionizing world. So we're getting close in the semiconductor industry. We're getting close to ionizing energy, as it were. And again, Pyrex glass is effective shield. And some of this, you know, you get to 13 and a half, the ultra violet, extreme ultraviolet, if you will, is presenting soft X-ray hazards. And again, this thing called inverse square law, if you double the distance, it becomes 1/4 the power. That works. I won't get into that too much, but let me know if you do have questions and I can help with it. And then again, how do we do surveys, whether we're perpendicular or we're facing the source? Again, ACGIH and the documents are a great help on how you approach these extreme UV hazards. So just to be consistent, I guess, across the whole non-ionizing radiation band, right? And the distances, right? The basics, whether, and again, this works even for ionizing, time, distance, and shielding. And so these are things, we can put shielding in, we can increase the distance away from sources, and we can reduce our time around them. So if someone were to be up on a rooftop and you could not afford equipment or you don't have the equipment, you could say, okay, don't spend any time over by that thing, that emitter, and reduce your time, increase your distance away from it. Keep your distance, don't stand there. That's a way of working with unknown objects, even if we cannot measure them. So we may be too sensitive to it. It may not be a high-powered emitter at all and one worthy of it, but if we don't know, we don't know. So that's one of the things you could consider. And then these are signs. So in US, I know in Canada, Canada tends to use the words caution, warning, danger. In the United States, we tend to go notice, caution, warning. So to us, danger means, you will be injured and you might be killed. Danger is kind of a too serious of a word for us here, but I throw out some of these. The symbol, if you look the notice sign, that's the international agreed upon symbol for non-ionizing radiation. What we call the point source emitter is the title of that whatever thing. And so caution or warning, we put it inside of a yellow or an orange or a red for danger. And so you could have the language typically underneath. The English that I've thrown in here is all up to you. That's not part of the standards. So you can do signs in your language. You could do them in multiple languages if you have that kind of society where two languages, if you will, like Canada, English and French being dominant. In America, a lot of times it's English and Spanish. So you're free to put whatever wording you want below it. I just threw out some various things, but if we put a warning sign up in the States, we mean keep out. So what we do is we call it lockout, tag out. So we're restricting access and we're not allowing anyone in that area unless it's been verified that the emitter is locked out and tagged out. So we use that to control. So that's kind of signs of what we do. I encourage you to look at that and that you put the correct sign up. If you oversign, then you can falsely alert people. And then when you do need to cry wolf, someone may not listen to you. So use the right sign for the right part of it. Normally, we use notice when we exceed the untrained worker limit. We use caution when we exceed the human exposure limit, and we use warning when we exceed the human exposure limit by a factor of 5 or 10. So that's kind of what we do. So signs are also part of your program. Measurements and monitors. I just throw this up for some of you that want to know, okay, what do I do to measure this stuff? As you might expect, getting stuff off the internet is not always the best thing. What we do in this world is we talk about accredited equipment. So the calibration and the facility have been accredited by an international accrediting agency. And in other words, they're making real products. So there's a couple companies out there, what I consider NARDA or Wave Control are accredited. And my personal favorite is Wave Control, even though that's not who I spent my career with. But at any rate, I just throw that out there so you can go visit these companies if you feel like you need equipment on it. So there's wide-ranging equipment. There's equipment, just as a point, there's equipment to measure and survey. There's equipment for people to wear if you feel like a wearable monitor is warranted for somebody, or what we call like area monitors, something like a smoke detector that would work and be useful in that regard. So depends on your safety program and what you're trying to control as to what kind of equipment you might use. And so last but not least on this, if you're going with consultants, obviously relevant credentials. I think memberships are important. Of course, experience always is. And communication. I always, if I go out, I always like to communicate what I'm doing and why. And I say in a lot of my quotes that, I'm really looking to, while I'm there, I'm looking to train you to be able to do what I do in the future. So I don't want you to call me back. I want to go out and do it and be done, something. So, and of course, is the equipment accredited? And failures. I think, failures is one of the interesting things that I ask people. So a lot of times, and this is one of those gotcha questions, but as a consultant, I think there are times where I have tried to get a client to do something and I have failed at it. And so I think failures are the most interesting part of this. And like I said, consultants, everyone thinks you hire a consultant and every company is going to listen to the consultant. And of course, that's not the way it works. And so if you have enough experience, I think you have experience with failures as a consultant. So anyway, and again, like I said, your success depends on your participation. So don't supervise me, participate with me is kind of the point here. And I think that's, again, if you hire a consultant, be involved. That would be my number one thing. I don't want you to just point me in the direction and have me go do it and then come back and brief you on how I did it. I don't think that's good for either of us. So anyway, with a couple of minutes left, I throw this up to now. Harshi will have we'll have this on the website, whatever, or they'll send it out or whatever. But I tried to put the links in here inside of the PowerPoint, and hopefully it works. But so I have the links to the site here. The second one, the ITU document, I think is a very good, even though it says, for workers at radio telecommunication sites, you might find the points very, very good just for general safety, even if you're at an industrial site. So don't hold back on that. And the beauty, I love it, is that it also comes in terms of Spanish and French, so not just English. All of the IEEE documents are available. You can go to this GET program and you just establish an IEEE email address, which is really easy. But at any rate, they allow you to download this. So from the IEEE, they just want to know who's downloading it. So this is some of it. And again, ACGIH, TLVs, those typically have a cost to them. But again, ICNIRP does not the first one. So I leave you with that. So that's kind of, I think, do it here. That's kind of my presentation. Again, I throw this out here. Any of you are more than free to email me if you have questions. You can go to the website, whatever, and then a poor joke at the bottom. But at any rate, that's, Hertz. So Hertz is the whatever. So anyway, yeah, technical report. I don't have any problem doing that. But email me and I'll send it to you if you want. I won't go through it here because time is short. So
Plus,
anyway,
it's an unreasonable expectation. You should not ask for the report. Okay.
Yeah.
All right. Question? Anybody? I'm looking at some of the question. What is the effect of Earth sphere on the non-ionizing radiation public limit? I can see many clapping also. Everyone. Right. Once again, the question is, what is the effect of Earth sphere on the non-ionizing radiation public limits? I'm just trying to think about the question. And Jake has a question. Let's see, go through. So, yeah, Bob, the question, did you get the question? I'm trying to think. Effect of the Earth spheres. The person may be talking about atmospheric radiation. Yeah.
Okay. Oh, there it is. Okay. I was not seeing that. So, the Earth has its own static magnetic fields. And so it's not an effect per se for most humans because the field is relatively weak. It is interesting to note that if you have a ship, that routinely sails long voyages, you can build up actually a magnetic charge on the ship, and that can interfere with very primitive navigation tools. And so you would have to degauss it. So degaussing is essentially wiping the magnetic field, resetting the magnetic field on the device. And that was something that we used to do a lot of when we had magnetic tape. So you would degauss the tape, you would wipe it clean and reuse it. So it doesn't really have an effect on people. It's really just more of a nuisance effect on radio navigation, I guess. So.
Okay. Great, thank you. We have a question from Utpal Bhavsar where he is asking, while handling permanent magnet, if workmen have magnetic part in the body, what is your suggestion?
Right. So, permanent magnets typically have a very strong field. And so I would, if someone has an implanted ferromagnetic, a magnetic material inside of the body, then I would recommend that they do not do that. So, that is, you're putting the wolf in with the hens. That's just something that you would not do. So I think in that case, I would ask if workers have implanted, medical or metal devices, and I would, kindly exclude those people from that kind of task because of the unknowns. So I just don't think that would be wise.
Great. Thank you, Bob. We have a Jake. Jake, do you want to unmute and ask the question?
Please, Maharshi, thanks, Bob. So yes. In terms of ICGIH limits and in terms of EU Directive 35, the Directive 35 states that workplaces must look after worker health and do assessments, and so too for the public. And of course, ICGIH is there for worker limits and public limits. What do you recommend a standard workplace? Like a telecoms business, guys that erect cell phone towers and all that sort of stuff. We've got workers going up and down the tower. you've got the tau that emits and can influence people of the public, as an example. But there's many other occupations or many other work in industries that have, like the induction furnaces, guys doing smelting, that sort of thing, that have equipment that generate magnetic and electric fields. Now in terms of occupational hygiene, you said you're an engineer. If we look at occupational hygiene, there's 5 key stresses. One of those are physical, and we look at non-ionizing and ionizing radiation. That we've got to assess risk in relation to EMF, non-ionizing radiation. How would you, given ICHIH, given EU Directive 35 and so on, should we be approaching the risk assessment protocol much like we'd be approaching the risk assessment protocol to noise or ionizing or heat, thermal conditions, hazardous substances, and so forth? Would you recommend us following the same sort of protocols and approach, and to assessing EMF risk? In other words, identify sources and then ultimately quantify, qualify as required.
Right. I mean, I would think you would identify the sources that you've considered significant in the workplace and what the risk is of them. I think, like I said, is that the standard itself, I know we haven't gotten into it here that as much, but to me, the standard has at least a 10 times safety factor. So years ago, when they were exposing animals to non-ionizing radiation, they found that with rhesus monkeys and squirrel monkeys that a level of about 4 to 8 watts per kilogram would, over time, would heat the animal as much that they would not want to do these mental tasks. And so it was a reversible behavioral effect. So years ago, they said, okay, well, if that's 4 to 8 watts per kilogram, we'll take a 10 times safety factor. And so we'll set our limits at 0.4 watts per kilogram. So I think, to me, the risk is to the employee, is they should understand is that the standard has a lot of a safety factor in it, and that as long as they comply with the standard, that we think there is little to no risk. And so to me, they need to be educated that the risk, you increase your risk when you go over the standard. And so here's the things that we've done. We've put up a barrier, we've put up signs. And so as long as you stay outside of that barrier, your risk is minimal. So, the idea of inverse square law of radiation, and you could include other different things in that, but I think educating them as to why you put a barrier up is because of the standard, and that as long as they comply with the standard, their risk is minimal. And I don't know if you do that with other physical hazards, but I think in terms of non-ionizing, that's what I would do. Does that help?
And then, so it does help. And one last question then, in terms of, I know the jury's still out on some other research points around EMF, the fact that, we are exposed to many hundreds more times the EMF than our grandparents were. I know that's the common understanding around the increased levels of EMF, and as the globe becomes more and more modern, and the Starlinks and the 5Gs and the electrical reticulation systems and so on, impact effects on things like circadian rhythms that haven't really been well, let's say, researched. What are your thoughts along those lines? So not necessarily, I know it's a IRC2B classification in terms of, I think, leukemia, but just in terms of other effects, like on the electrical, let's say the bioelectrical system of the human body and things like circadian rhythms.
Well, I think if you actually look at IEEE and ICNIRP, and I'm more familiar with IEEE on all the papers that we review. So I know I kind of tend to drift towards the thermal effects, but they actually do have papers studied on the circadian rhythm, and there's no demonstrated effect to that, to these exposures. So I know what you're saying. even though we've got, 40, 50 years ago, we didn't have all these cell phones and Wi-Fi and Bluetooth, and we have all these things now. But the existing belief is that as long as these cannot create a measurable increase in tissue temperature, then quite honestly, no effect has been proven. No health effect has been proven. And that's everything from, from cancer initiation to circadian rhythms to electrosensitivity to all of these, any health effects. So right now, like I said, believe it or not, that's where we're at. And so that's why the standards are so similar to what came out, let's say in 1982 from ANSI. The standards are all very similar to that because no health effect has been proven, consistent health effect, from exposure to these fields as long as we comply with the standards. And that's where we're at. So, we studied, the effect of 5G on monkeys, whatever, no, we probably haven't because we don't do that anymore. And, it becomes that catch-22, as we'd say in American slang is, you want to prove the effect on human, but we don't get any human volunteers, right? Nobody wants to be part of that program. So, that's kind of where we're at. So we honestly, we set and base standards based on what we know, not what we don't know. We can't do that. And so that's where everything is. And I think it's interesting to note, again, ICNIRP and Safety Code 6 and IEEE, that we all have these different groups, but all of them are presented with the same science results and papers, and we all end up with the same limits. So, in the internet world, we can't hide anything. So, our Panza is, in the same boat as the rest of us or whatever, blah, blah, blah. Everyone looks at the same papers and sets limits, I think, the same way. So that's where we're at. Does that help?
Bob, it does help, Bob. I'm going to leave you with a thought. It's not a question, don't answer. But there's a gentleman by the name of Joel Moskowitz out of UC Berkeley, I believe, that actually puts out. He references quite a lot of research and work in the area with some interesting, let's say, deductions, assumptions, and so on out of those research papers.
Yep. We get some very educated people that look at things a different way. And like I said, we're very transparent in the committees as to how we accept papers, and we look for, oh gosh, what am I? I'm losing the word. But we look for the same result from a different researcher. And you know what I mean? Like we're looking at this, gosh, at any rate, we're looking for this commonality of results from two different researchers of coming to the same conclusion. So we would not look at just one person, this Mr. Moskowitz, if you will. We'd look for somebody to actually redo it and come to the same results as him. And then it's interesting. Then we have scientific.
Wonderful. Excellent. We have 2 minutes left, and we have 2 more questions. We have, you mentioned not to include workers wearing implanted medical devices in your safety program. What's your approach then, trying to measure for every single situation and then making decision of implanted devices rather than making more stringent? I can answer, but you can answer that.
That's an interesting question, and one that, like I said, years ago, I did a survey with the US FAA. And we went all around various radar sites and communication sites. And one of the things that we noted is that if we had a building or a piece of equipment that consumed more than 100 amps of power line frequency, if it was consuming that much current, that it could start to approach the medical device limits. In the US, almost every commercial building has some area where the power comes into the building, that almost everybody should post a sign to keep pacemaker wearers out of that area. So the medical device people. So that would be like one rule, if you will. So we don't try to go everywhere they would go, because like for the normal office environment, it's quite safe for a medical device wearer. But like I said, where power comes into a building, that would be something where I would do that. And so I throw out the number that we have developed in the FAA is 100 amps. So if you're consuming more than 100 amps from any device or building at 50, 60 hertz of power line, you're going to get close to the medical device limits. So I'll leave that.
Excellent.
And then last one, the EMPs before we go. Yes, that bolt of, if you will, electromagnetic field is there were some health effects from people who were out on a ground plane doing EMP testing, and standards today do not allow that. So we have a 100 kilovolt per meter peak limit. You cannot be over that limit. So that precludes from having people out in those areas. So I would not have people in an EMP testing area. It would exceed the standard. So.
Excellent. Very good. I think lots of discussion questions. Bina is asking whether this recording will be available. Yes, a recording will be available. We are creating on IOHA website member-only page, and in that presentation and recording will be available, which all of you should have access. All right. So that was the last question. What we do typically is, first of all, once again, I would like to thank Bob for doing this second time. I know it's a time-consuming task. You have got many things to do. Finding time to provide such a meaningful education in an area which is not known to many, including me, and therefore this education that you have given to us is much more valued. So thank you, Bob.
Quite welcome.
Feel free to leave your comments in the chat section, because when we recognize Bob's contribution, we will put your comment in from the chat section. What typically we would like to do in every webinar is, at this point, you can show your video if you feel comfortable, if it's past midnight, and if you don't want to show in your country, we will understand. But if you would like to show your video, Rita or I will take a screenshot and keep this into IOHA information. Okay, everyone? Yeah. All right. Yeah, very nice. We have.
And Robert, if
Yeah.
I can ask you to unshare your screen.
Yeah. Yeah,
Great.
very nice. Super. Boy, great to see so many people. Yeah. All right, maybe a few more seconds to share your screen. Sorry, not share your screen, share your video. Okay. Maybe Rita, you can now take the screenshot. Yeah, everyone.
Thank you, everybody. I've got it.
Very nice. Hey, everyone, thank you so much. We'll be seeing you in the next webinar. If you would like to offer any webinar, please send us the information, which webinar you would like to offer. If you know of a speaker who is an outstanding speaker like Bob and would like to talk about subjects like this, by all means, please let Rita and me know. Okay. Thank you so much, everyone. Have a good evening, night, day. Okay, Bob, once again, thank you. Bye, everyone.
Goodbye. Thank you.
Rita.